We're going to finish section 3.3 today. 3.3 is about increasing and decreasing functions. And we had encountered some of these ideas of looking at where derivatives are either positive or negative. And we had something called the first derivative test. We had all sorts of beautiful colors in this slide that talked about the first derivative test and how we identify where functions are increasing and decreasing, and then how that applies to them being a local or minimum, or giving us a local minimum or local maximum. The question that we had done already was this one, example number 1. If you remember, what we did is we're looking for critical numbers, and so we took the derivative, and then we set it equal to 0, and we solved it. This was a very simple derivative and everything. We recognized that. But I was trying to show you that all the things that you already know about this function work with this derivative test as well. You created a number line, and on the number line, you have the number 1 noted, and then you choose a test point in each of the intervals. After you have your test point, you use those test points inside of the derivative equation, looking to see whether or not you get a positive or a negative value out of it. We weren't really so much cared about the value itself, but with the sign of it, whether it's positive or negative. If the sign is positive, then that means the graph is increasing on that interval. And if the sign was negative, it was decreasing on that interval. So if your graph is increasing, which it was, and then decreasing, which it was, this means that you've got a maximum on that point. Okay, everybody remember how we did that? Okay, because we're going to do another one next. All right, so this is our next problem. We have a function y equals x plus 4 over x, and all the directions are the same as the one that we did last time. So we're supposed to find the critical numbers and then test whether or not it's a max or a min. So what do we do to find critical numbers? Derivatives. All right, so let's take our derivative. It might be worth noting that this is the same as x plus 4x to the negative 1. It might be easier to take the derivative that way than to take it with a quotient rule. All right, so what is the derivative of x plus 4x to the negative 1?
1 minus 4x squared.
All right, so 1 minus 4x to the negative 2, which is the same as 1 minus 4 over x squared. Right? Does that look good? Because you guys already told me what to do next. What was it? Set it equal to 0. Now, let me note two things here when I set this equal to 0. There's two ways to solve this, I should say. One way to solve this is to get a common denominator and so forth. Okay, I'll show you that in a minute. Another way to solve this is we could actually go from where we are, and we could do some cross multiplying. So if I move this 4 over x squared to the other side, and then I have x squared equals 4, because I cross multiplied, then what does x equal?
2.
Or, right, plus or minus 2, so positive or negative 2. That's 2 of my critical numbers. There's one other critical number. Do you know what it is? 0. We need to use x equals 0 as well. Why do we have x equals 0? Where's that coming from?
The denominator, you can have 0.
Right. We actually need to find out where the derivative is 0 or where it does not exist. And the derivative does not exist at x equals 0, because that's where the denominator would be 0. I kind of like it on this one to do that way. Let me show you the other option here. The other option is that we could actually take that 1 minus 4 over x squared and get a common denominator, which means that would be x squared over x squared for the number 1, right? So you'd have x squared minus 4 on top, x squared on bottom, and then you'd have x minus 2 and x plus 2 on top, and x squared on bottom. And that's nice too. I mean, it factored really nice and clean. I'm going to get the same answers, right? Because if this numerator is equal to 0, I'm going to get x equals to 2 and a negative 2. And if the denominator is equal to 0, I get x is equal to 0. I get the same critical number. So there's 3 critical numbers that I'm going to be working with. I'm going to be working with 0, negative 2, and positive 2. All good so far? Okay, so what do I do with those critical numbers? Well, I need to test around them. So I like to put them on a number line to give me a visual. I'm a visual learner. That's something that I have discovered about myself later in life. And so I tend to draw pictures whenever I have the opportunity. You don't have to do this with pictures, but it is helpful for some. So I'm going to put my negative 2, my 0, and my 2 on a number line, and I need to test points around them. So I need a value before negative 2. So what do you want to try? Okay, negative 3. How about between negative 2 and 0? Okay. and then 1. Okay. And then you do 3? Okay. So if we have 3 critical numbers, which we do, how many test points are we going to have? 4. We're always going to have one more than the number of critical values we have. However many critical values or critical numbers we have, we're going to have one more test point than that because we have to do the intervals around them. So we are going to test each of these points in which equation?
Like the original.
Is it the original or is it the derivative? This is the derivative. So let's, it's okay, good guess. Come back over here and take a look at what the derivative test says. The derivative, I know there's all kinds of markings on this, and they made sense when we did them before. Now that just looks like pretty markings all over my screen. But when we looked at this before, those markings that we did at the very beginning that are circled in red and circled in blue tell us that you want to talk about whether or not the derivative is positive or the derivative is negative. Because if the derivative positive or the derivative is negative, it tells us whether the graph is increasing or decreasing. And that's our concern. We want to know if the graph's increasing or decreasing. So we're going to take our values and we're going to plug them into the derivative equation. So I'm going to do y prime of -3, y prime of -1, y prime of +1, and y prime of +3. And we're going to test each of them into the derivative equation, which I'll use the one here that is written with the x squared in the denominator. So I'm going to have 1 minus 4 over -3 squared. So real quick, we don't even need to know the value, we just need to know whether it's positive or negative, right? So what's -3 squared? 9. 4 over 9 is less than 1. Yeah, it's less than 1. So this number is going to be positive. So this is a positive number. Okay, we'll deal with the picture of what's going on here in just a second. What about when I put in the value -1? I am going to get a negative number, right? Because -1 squared is 1, 4 over 1 is 4, and then 1 minus 4 is actually a -3. So this one's negative. What happens when I put in the number 1? Yeah, because the denominator's squaring things, right? So I still get a negative. And then the last one, putting in the number 3, what happens? It's a positive, just like when I put in the -3. So this one's also a positive. Okay, so in terms of my number line down here, I've just found out that when I put in the -3, the graph was positive. Positive means the graph went uphill, it was increasing. So we went up. When I put in -1, the graph gave me a negative, so that should be a decreasing graph. When I put in +1, I also got a negative, so that's a decreasing graph, going downhill still. And when I put in the +3, I had a positive, so I had an increasing graph. So take a look at the picture down here. If I am increasing and then I'm decreasing, what happens at x equal -2? This is a max. We'll write our answer out in a minute. Over here, if I'm decreasing and then I'm decreasing, what happens at 0? In this one, there is an asymptote, but at the very least, we know that it's neither a minimum or a maximum, right? So this point is actually neither, but you're exactly right, Blaine. It's because on this particular one, there's an asymptote there. Okay, then how about when we're going to decrease and then we're going to increase over here at 2? That's a minimum. So they do tell us to classify the locations as max, mins, or neither. So in my classification, I will need that information. So let me carve out some space by erasing. We'll put it right over here.
So do you want to put neither?
For the x equals 0, yes, because they do tell you in here they want you to classify each of them. So we have a local max at x equals -2. We have a local min. You could also call these relative mins and maxes, but we have a local min at x equals +2, and we have neither at x equals 0. And if you want to be more specific, you could also identify that's an asymptote, but you're not asked to. The other thing, too, to notice is that I'm just writing down the x values. It says x equals, x equals, x equals, because they asked me to find the critical numbers, not the critical points. If it asked me to find a point, I would need an x and a y ordered pair. Okay. Any questions on this one? Okay, let's do another one. This one's directions are a little different. This one says to find by hand all the asymptotes and extrema and then to sketch the graph. So we're going to have a picture of this thing when we're done. And we're going to be able to confirm it with our calculator, so that's fine. But we don't need our calculator to be able to do the graph for this at the beginning. We're just going to use it as a testing value, or a testing, or a check step, basically, like at the end. The first thing it talks about is asymptotes. What kinds of asymptotes are there? Vertical, horizontal, slant. So looking at this equation, which ones will we have for this equation? Vertical and horizontal. Let's start with vertical. Where do I find vertical asymptotes, or how do I find them? What is? Good. I set the denominator equal to 0. So how am I going to find out where that denominator equals 0? What do I do? Factor. You bet. How will this factor? X minus 1 and x minus 3. And then if we solve that, what values do x equal? Does x equal? 1 and 3. So we have two asymptotes that are vertical asymptotes, x equal 1 and x equal 3. If you want to, you can sort of be working on creating your graph as you go by putting in the pieces you know as you go. So I'm going to draw my asymptotes in it as red, and I've got an asymptote, vertical asymptotes at x equal 1 and at x equal 3. You could wait to do that till the end too, that would be fine, but we can do it as we go. You mentioned there's also horizontal asymptote, I think, right? So how do I find my horizontal asymptote? Basically, I look at powers to start with, right? The degree of the highest power on top is a 2, and the degree on bottom, the highest power is a 2. So since they're the same, they're equal powers, what do I do? I look at the coefficients. Good job, Summer. So the coefficients then for the highest degrees, in this case, are both the number 1. It's 1 over 1. So this is a horizontal asymptote of y equal 1. So over here on my picture, I will have a horizontal asymptote here at 1.
Explain that again.
Well, this was back from chapter 1. In chapter 1, we talked about asymptotes. When we look at horizontal asymptotes, we look at the highest degree. When the highest degree are the same, which these are, we do a ratio of the leading coefficients. So we look at the coefficient of the highest degree term. So the coefficient of x squared on both of those are 1.
Okay.
If one of them had been, say, 7 or something, then that would be the value we would have in front. So it's the coefficient in front of them. These are both 1. Okay, is everybody good on the asymptote part? Okay, so that's actually kind of like a review thing that we've done, right? I mean, we've done asymptotes before. It's been a little while, though, to really talk about them in this sense. All right, the next one is extrema. That's this section, actually, right? Talking about, well, actually, last section and this section, 3.2 and 3.3, talking about extrema. So to do extrema, what do I do? Right, because I'm looking for the critical points. I need to find critical points, and the way I find critical points is by finding a derivative. So I need the derivative of this function, and this function is a quotient, so I need the quotient rule. All right, so quotient rule, what do I do?
The denominator times derivative of the numerator.
Okay, so my denominator looks like this. What's the derivative of my numerator?
2x.
Good. Then what do I do?
Right here, denominator.
I'll subtract. What will I subtract?
Here, x.
X squared times derivative of the denominator, which is 2x minus 4. Good. And all of that is written over
Denominator
denominator
squared.
squared. Do you guys realize how comfortable you now are with derivatives? I kind of think it might have something to do with that quiz that some of you have taken multiple times. Just a thought. All right. Let's simplify that numerator, because that's actually not on the quiz, that simplification, that algebra step. All right, so what do we get with the first piece when I simplify?
2x cubed minus 8x squared plus 6x.
Good? Somebody else simplify the second one. I'll start. Here's a negative. What's next? Good, thank you. Now, it's not minus 4x squared, though. It'll be plus. Yeah, good. 4x squared is a positive on that one. all over the x squared minus 4x and plus 3 quantity squared. Nice. Okay, then, that numerator has some things that will simplify. What simplifies first?
2x cubed and negative 2x.
Yep. Those go away. Good. Now what? Well, there's an x squared and... Yep, so there's a negative 4x squared left. And what else? Plus 6x. All over that same x squared minus 4x plus 3 squared. Okay, so we've got the derivative now. It's all cleaned up and looks real nice. What do I do with it now?
Solve for 0.
Right. I set it equal to 0, yeah. So setting it equal to 0 is equivalent to what? Having what equal to 0 in this type of a function? The numerator. And then we do the denominator separately because we want to find out where the denominator equals 0, why.
That's where
That's where the asymptotes or holes are. So that actually could change whether the function's increasing or decreasing at those particular points. And if we're looking for increasing and decreasing kinds of functions, that's part of the information we're looking for. Taking a look, too, at that information, we already did that part, right? We actually did that when we found the asymptotes, so we don't need to do that piece again. We now only need to concern ourselves with where the numerator is equal to 0, because we've already done the denominator, actually, since it's the same denominator as the original function. The squaring doesn't change the zeros, so. All right, so what can I do with that denominator, then, to find out where it's equal to 0?
You can factor out a negative 2x.
Right, and you could either take out a negative 2x, or if you wanted to just take out a positive 2x, you could do that too. Honestly, if you just want to take out an x, it would be okay. Any of them will work. I'm going to take out the negative 2x because that's what Blaine suggested, and he was the one I heard. So if I take out a negative 2x, what's next? Or what's left? Two x minus 3. Very good. Thank you, Lanisha. All right, so then I've got these two pieces equal to 0, so what do? I solve each of them individually, right? So the first one will equal 0 when x is equal to 0. The second one will equal 0 when what? At 3 halves, right? Yeah.
Negative 3 halves. No.
Positive 3 halves, actually, on this one. Yeah. There it is. All right, so we have x equal to 0, x equal to positive 3 halves. We have these two spaces, and we have these two values that will all go into a number line. Okay? So here's my number line. My number line is going to include, look, 0 is my smallest, I guess. Then I had 1, and then what? 3 halves, and then 2. Now these are a little bit more tight values together. They aren't spaced out as well as the last ones were. So what was that? It was a 3 instead of a 2, you're right. Okay, so we need to have a value, values between these. So what's the value you'd like to pick before x equals 0? Negative 1. How about between 0 and 1? 1/2. And I'm going to just use these as decimals for the moment. We're going to use our calculator to find these values for us. What about between 1 and 3 halves? 1 is 1, 3 halves is 1.5. 3/4?
No, point.
3/4 is smaller than 1. 1.25 would work, though, right? Because this is the number 1.5, so you need something between 1 and 1.5. So 1.25 would work. How about between 3 halves and 3? 2. After 3? 4. All right, so grab your calculator, and I'll remind you how to do this with your calculator. You're plugging these into which function again? The derivative. Good. So we want to plug these into the derivative at negative 1, at 0.5, at 1.25, at 2, and at 4. So you can do that by taking your equation, put the derivative equation. This one right here is probably the nicest one, the cleaned up version right here. Make sure if your calculator requires you to that you put the entire numerator in parentheses. Okay. And then you can put that in y1 in your calculator, and then you can use your table. You can go into your table and you can enter all 5 of those values, because we did have 5, that's quite a few. all 5 of those values into your table and find out what you have. And again, I don't really care what the number is. What do I care about? Whether it's positive or negative. That's the important piece of information. So fill in all 5 of those. I'll give you guys all a chance to write those down, and then I'll correspondingly ask you what they are. Is everybody having success with their calculator, getting it to do what I'm asking? Any questions with that? Yes, here. I'm sorry. So you put it here.
I didn't.
Okay, put the equation here.
This.
No, the derivative. We're working with the derivatives of this version of it. And then after you do that, just pause for a minute, I'll show you. You would go into the table, but you hit second table. Oh, it's not liking it because you don't have the equation there. But you'll hit second table, and then you can enter these values all into the table.
These ones.
Mm-hmm.
Okay.
Yep. Okay, go ahead and enter that, yeah. All right. Has everybody had a chance? I know Kelsey's still working, but everybody else have a chance to get those values in? What happened when you entered -1? You got a negative? How about 0.5? Positive. 1.25? Okay. 2? And 4? Okay. Okay, so in terms of a picture, I'm going to draw what that is. So a negative is a decreasing. Positive is increasing. Positive again is increasing. And then the last 2 negatives are decreasing. This is what they look like. So the first point at x equals 0, what's happening? The local min. How about at 1? It's neither because it's an asymptote, right? How about at 3/2? That's a max. And at 3? Neither, and it's again because we have a asymptote, right? Okay, so we've got 1 local min, we've got 1 local max. Everybody good so far? Okay, we've found all the pieces of information we're asked to find. We're actually supposed to now sketch a graph with that piece of information. All right, so let's start with the left-hand side of the graph. So before the x value of 1. Somewhere over here at x equals 0, I actually need to have a minimum point. And if I'm going to have to plot the point, I actually need to know the x and the y. So when x is equal to 0, what in the world is y on this particular graph? How can I find it? Plug it into the original equation. So take a look back at that original equation. If you plug in x equals 0, we get 0 for y. So y of 0, the original function y, or original, did we call it y? It was called y. I used f's over here, that's okay. I actually have 0. So my point on my function, I'll use my graph in blue today, is 0, 0. That should be a local minimum value. Well, that sort of seems weird, right? Because the way that I would normally think with all these asymptotes everywhere to draw the graph is that this point would sort of come up towards here, but then this point would come down towards this one. That's what we see often, isn't it? But it's not what we see on this particular graph. In fact, before x equals 0, it is supposed to be decreasing, because it said, right, it's negative. You see that green line at the top there? I'm supposed to be decreasing. So it is reasonable for this graph to be like this. But it doesn't continue to go down after that, because it says that when I'm between 0 and 1, I should be increasing, which means the graph must do this. And that looks just a little bit odd. Now, one of the,
You plug those 4.5 in the original equation,
I didn't plug all 4 of them in right now. I just plugged in the number
Yeah.
1, the x equals 0.
so it makes sense.
Yeah, you don't need to plug in the 1 and the 3. because those particular points are asymptotes. But we are going to plug in the 3/2 in a moment. You're right. Yes. You might be bothered by one other thing here. You might be bothered by the fact that that blue curve that I just drew crossed an asymptote. Is anybody bothered by that? It's a little odd. It doesn't happen very often, but it is possible for it to happen. What you want to remember is that horizontal asymptotes talk about end behavior. They talk about what happens on the end of the graph. So can you cross a horizontal asymptote in the middle of the graph? The answer is actually yes. It's just that on the ends of the graph, it's got that asymptotic behavior. And it does here. This blue part over here towards negative infinity is getting close to that horizontal line, so that's okay. So everybody good with that piece? Okay, the next piece is actually at the between 1 and 3, and that's going to we can take a look at our x value of 3/2. So just like Jason's was asking about, that 3/2 value also now needs to be plugged back into the original equation. So my suggestion right now is to take the original equation that we were given and put that into your calculator instead of the derivative. So go ahead and change your equation from this y prime in your equation and put the original y in the equation. So x squared over x squared minus 4x plus 3. And then go back and plug in 3/2 into your table. Or you can type in 1.5 if you prefer. What do you get? -3. That's correct. All right, so we have at 3/2, and 3/2 is about right here, right? Because it's supposed to be 1.5. This is the vertical asymptote at 1. This is the x value at 2. So this is where we've got the value right here for 1.5. And we're supposed to be down here at 3, -3. And that point is a what, max or min? It's a max, which means it needs to be the largest value. And these asymptotes, they do have to get close to them. So it looks sort of like a tilted parabola or something. I mean, it's definitely not a parabola. It definitely opens downward, though, and it gets close to those asymptotes, but it's not symmetric, is it? It can't be because of the values that we're using and being given on the particular parts of problems we've already done. Okay, our last piece of information, if you were working in an algebra course, what you would do is you would actually test a point over there. That is, you would say, hey, let's try x = 4, and just plot it, and then we'd use that information to draw the graph. And there's nothing wrong with that, but we don't actually need that. We do know what the graph is doing on that part of the interval, because we tested x = 4 into the derivative, and we found out the derivative was negative. What does a negative derivative mean the graph's doing? Decreasing. Which means that I need to draw something that's decreasing over here and that gets close to that horizontal asymptote on the end. Will the graph be above or below the horizontal asymptote? Got to be above. The only way to draw the graph so that it's getting close to the asymptote on the end would be for it to be decreasing above the line. If it were below, it would have to be increasing. So I don't even need a test point over there to actually know that the shape of the graph, more or less, looks like this. Now, you should have, if you plugged in the 3/2 just a minute ago, the equation in your calculator. I'd like for you to graph it. Go ahead and hit zoom 6 or zoom standard or put in that -10 to 10 window. Does your graph look like this? Does that look good? And you did it all by hand with calculus. Okay? Any questions?
So why did we add that last one?
Well, it's part of the graph. That's why it's there.
So you said, okay.
Yeah, we're supposed to be sketching the whole piece of all of the pieces of the graph. And we know that piece of information because we tested the value 4 originally into the derivative, so we knew it was decreasing.
Okay.
Okay, last question in this section. This one is correct. This isn't the one I was telling you about before class started. Everything's fine on this. I chose the hardest one in your section on this one this time. Lanisha came and talked to me about graphing some of them in 3.2 this morning. And in 3.2, I chose the easiest one. And we did that one in class together, and you guys had 3 more after that. You've got 3, I think, again in this section that you're going to do. But I picked the hardest one to do for you. Okay? Sound good? You're welcome. All right, let's take a look at it. We got a lot of information here that we're supposed to sketch a picture for. I know that sometimes these can look a little bit overwhelming, but if you just get started with what you've got, things usually fall into place pretty well. So the first piece of information, first two pieces of information are giving me simply points on my graph, right? Yeah, so we're just going to plot those. So we're going to start with that. We've got a graph. The graph has the point 0, 0 on it. And it has the point 3, negative 1. Okay, so far so good? Okay, so we've kind of taken care of those. I'll mark them off. The next pieces of information, I'll talk about derivatives. Now, derivatives tell us where things are increasing and decreasing, right? So when the derivative is negative, what does it tell you about the graph? It is decreasing. So this first one tells us that we've got a graph that's decreasing after x equals 3. So x equals 3 is that last point 3, negative 1 that I just plotted. It needs to be decreasing after that somehow. Now, I don't know yet exactly how. I'm going to sketch something, but you're all using pencil, or at least you would be on your homework. So if you sketch it wrong, and we're probably going to sketch it wrong to start with on this one, we may have to fix it later. Okay? So let's just say I'm thinking, okay, you know what? We're just going to go like that. Nothing real special, nothing real particular, just draw it downhill. All right, it tells us then over here that the derivative is positive. Okay, so I did this piece, at least I tried to. It tells us the derivative is positive for x less than 0 and between 0 and 1 and between 1 and 3. Good gracious, it's positive a lot of places, isn't it? What does it mean for it to be positive? It's increasing. So this is telling me that the graph is increasing before 0, it's increasing between 0 and 1, and it's increasing between 1 and 3. Okay, so, I mean, it could just be like a straight line upwards with that piece of information, right? I mean, that's a possibility. But real quickly, we found out some more information about the points. Right here it says f prime of 0 is 0. What does that mean? Not an asymptote. Not a hole in the graph. It could be a max, it could be a min. What else could it be? Nope, not a sharp turn, or that derivative wouldn't exist. Okay, that's the f prime of 1 doesn't exist part. You guys are kind of mixing in here, but what's that? That's the very minimum we know right there. We know that we have a horizontal tangent line there. We get horizontal tangent lines when we have slopes when the slope is 0, right? That's what that's telling us, slope is 0. And it could be a max. It could be a min. We know it's not a max or a min, though, at 0. Why? That's not why. We could have a point there and we could still have a max or min. In fact, we would.
Well, because it's positive on both sides.
Right. Remember that first derivative test told us that if the graph is increasing and then it continues to be increasing, you do not have a max or a min there. So at x equals 0, I don't have a max or a min. It's not possible because it told me that the graph is supposed to be increasing before 0 and increasing after 0. Do you remember a graph that I drew that did that once? I've drawn it a couple times now.
X cubed.
The x cubed graph. That would have that slope of 0 there like we're wanting. So I'm thinking we can draw something kind of like that. It doesn't look very flat there. Let me try it a little bit flatter. That's a little bit more convincing. Okay, so this is the before x equals 0. This is the after x equals 0 before x equals 3. I'm sorry, before x equals 1. And it is increasing, and it's increasing, and it's flat. Is everybody good with that? That takes care of this piece of information and these two pieces of information. Now, it's still supposed to be increasing between 1 and 3. But before I get there, this one also says f prime of 1 doesn't exist. How do you get derivatives to not exist? Asymptotes, holes, or what? What's the third one? Sharp turns, cusps. Okay, a place where we have this sharp change. What do you want to do? You have a choice. You want to do an asymptote? Okay, we'll do an asymptote. All right, so I'm going to draw it in red. We'll draw an asymptote there at 1. You can either let this graph that you just draw, in fact, the way that I did it, I'll just let it stop right there with the hole. You could also just make it go all the way up and continue an asymptotic feature, right, so that it continues up straight.
Got your hands
That'd be fine,
for
too.
this one, the fact that it can be an asymptote, hole, or a sharp turn. Wouldn't a sharp turn be ruled out, considering that from 1 to 3 it has to be increasing? And for a sharp turn to happen, it would have to somehow go down, correct?
It wouldn't necessarily, it would just have to change how steep it was. Like, for instance, I could have it going, like, here's that piece right there, and then I could have it go like that.
Okay.
So it's not as sharp as what you were describing, but it's still sharp enough that the derivative wouldn't exist. So yeah, you still could have that. The graph is supposed to be increasing, however, between 1 and 3 as well, right? So, in fact, you know what, let me do this. I'll go ahead and draw this up like this, so that it's not so it's quite so distracting. All right, so it says that at f prime of 3, we're supposed to have a derivative at 0. Or at f of 3, we have a derivative at 0. What does that mean this point's going to be doing? What does a derivative of 0 mean on a graph? Max, min, or horizontal, a flat line, a tangent line that's just flat, right? It could be neither, but it could be, it still have a tangent line that's flat. Well, this graph is supposed to be increasing from 1 to 3, and we know it's decreasing from 3 on. So what's really going to be happening at 3?
Maximum.
It has to be a maximum. That's the first derivative test. If it's increasing and then it's decreasing, we'd have to have a max there. And our maximum there, it needs to be a smooth maximum. So this turn, this way that I drew it before, where it looked a little bit sharp, can't work. Oops. And we need to have doing something like that. Because it's supposed to be increasing from 1 to 3, decreasing from 3 on, and have a derivative of 0 at that point. So a sharp turn would not be allowed at that point, because the derivative is supposed to be 0, which means it needs to be smooth. Any questions on that one? Alrighty.